visible mixed pebbles.
Okay.
Draped by the sand. Yes, yeah, all good. So we've done the Niskins, have we? You got the Niskins logged?
Hey everybody.
So with the scoop,
Good morning from RV Falcourt 2.
With the scoop, please, and could we target that big
I'm excited to be welcoming you to another dive.
So we go.
You're watching a
I'll do the
live
starboard
feed from
boxes there
RV
then.
Sebastian. We have just touched down on another site, so our second site for Rayas Delta, located just east of the Grand Island of Chiloé.
Yep, that's good.
This is a live feed from one of our cameras on ROV Sebastian. So it's a remotely operated vehicle that's attached to our research vessel, Falcourt 2.
Can you put, dive mode
And this
in
big
there?
technical thing that's
Wherever that
covering up
camera
about
is,
half the
it's,
screen on the left
to the
is
right
something
side,
called a
you know what I mean? You
vibracore.
have it up right now. I guess so.
It's a really unique instrument that allows
we need
us
that camera
to
where it's,
take
like, on the right
really,
side
really
with the,
long sediment samples. What was that, Zach?
Can we get that camera that we usually have here, the one that's
I got it here.
HD1?
just where I can see my arm and stuff?
Yeah.
HD4, I think it is, maybe.
Oh, core cam? Yeah.
I've got it here. So.
Yeah, that one. Thank you.
Sorry, I forgot to do that.
All right. And this morning we will be doing some more geological sampling. And with me in the room here today, I've got Claude as my pilot and Zach as my co-pilot. And then behind me, I've got John Fulmer, lead tech. Whoop, whoop. And then I've got a whole team in the mission control room of marine biologists and geologists and paleomorphologists. You name it, we got them. And last but not least, I've also got a wonderful watch lead here with me, Dr. Sebastian Watt, who is also the chief scientist for this expedition. And so in a few minutes, he's going to introduce himself. We're going to just finish up this little sample here.
Number one. Zach.
Yep.
You see the one?
I'll switch the camera feed over for you so you can see the scoop bag a little bit better.
The one next to the yellowish. There, that one. Yep. If you can get that in, that'd be great. Thank you. Okay, thanks, Sophia. You
1 second, Seb. I'll switch you over. All right.
too big, Zach.
Passing it over to Dr. Watt now.
Okay, thanks very much, Sophia, and thanks everyone who's joining this morning. Excited to be on another ROV dive on this expedition. We're packing them in this week and finding something new every time. So for those of you who've joined us previously, and I can already see there's a few of you on the chat who've seen our previous ones, so thanks for coming back. You'll see that this looks pretty similar to the seafloor yesterday. But there's even more of this white material, which is what we're trying to recover in this first scoop bag. I think this white material, based on what we found last night, is pumice samples derived from a volcano just inland. And so where we are is in southern Chile, in this sort of inland seas of southern Chile between the Isla Grande de Chiloé and the continental coastline. And we're sampling here off a river delta called the Rayas River system. And just, if you go upstream from the Rayas River, you'll arrive at valleys that drain directly off a volcano called Chaitén. And Chaitén had a major explosive eruption in 2008, which transformed the landscape in this region. This blanketed the hill slopes with ash and coarser volcanic material. You can see I think what is a fragment of that volcanic material there, a big grain of pumice, I think, but we will see when we get this on board and can look at it properly. So I'm quite excited to see what that sample is when we bring it back on board. So Zach, yeah, if we could I think if we could do a second scoop back, please, Zach, but targeting this sort of pebbly lag here. at this
On the
site.
west side there?
Yeah. So yeah, the Chai-10 eruption devastated the landscape, and when you deposit all this such large volumes of volcanic sediment on the land surface, particularly on the steep slopes that characterize this region, so it's very sort of mountainous, rainfall can remobilize that, and this is a wet part of the world. And this was what was seen in the days after the Chai-10 eruption. Rainfall rapidly remobilized all that material, and that was channeled down into these river systems. It overwhelms the capacity of those river channels, particularly actually in the next river to the south, the river called the Blanco, which we'll be moving to in the next few days. There is a town on the Blanco Delta called Chai-10 as well. And Chai-10 was inundated by these sediment-laden floods in the aftermath of this eruption. The entire town was evacuated, very extensive destruction across a lot of the town. The town has actually been rebuilt in the same location, and there are people there today, and we'll actually be welcoming some groups from the town on the ship in a few days' time, which is really exciting. But what we're seeking to understand here, when these sediment-laden flows that we call lahars travel down these river valleys and reach the coastline, they slow down as they reach lower gradients and they deposit their load. This is what flooded through the town of Chai-10, and they also extended the shoreline. There was such a high volume of sediment, they essentially built out a delta in hours to days. So they really transformed the coastline. But what has not been studied or previously understood is how they impacted and potentially transformed the offshore environment as well. So we're seeking to understand how this material is distributed in the marine environment, what impact that has on the marine environment in terms of life and ecosystems, how those systems might recover or respond to those changes. And we're also interested if we can understand that sort of imprint of the Chai-10 eruption in the marine geological environment. Can we use that to look back in time to also understand earlier events and the previous history of volcanism in this area? So there's a whole sort of set of linked questions that we're interested in. So we're working our way through a series of study sites, moving southwards, gradually moving towards Chai-10 town in a few days. And then we'll be moving away again further southwards, right out towards the open Pacific Ocean, the continental margin in this part of Chile. And at each site we're doing seafloor mapping, subsea floor imaging, and then we're collecting samples to understand, to characterize that seafloor that we have mapped and imaged. So it's important to sort of combine all these data sets, all these different sources of information to arrive at a more complete understanding of these processes and systems. So this site, we've moved quite close to the margin of the Rayas Delta. We're really, from the ship we can see the river mouth, maybe just a kilometre away, or perhaps even less. And we're at the foot of quite a steep slope here that is marked by large-scale dune-like landforms, and we're just at the sort of margin of that. So we're seeking to understand the nature of those landforms, any recent input following the Chai-10 eruption. They seem to be deposited on older pebbly surfaces, which must represent previous very high-energy transport events. And we don't currently know the age of those events, but we hope to be able to use the data sets that we get on this expedition to get an understanding of the evolution of this delta system through time and how that has been impacted by volcanic processes. So we've just got the second scoop bag there. I think, Zach, I think we should try to move a little bit. And if we could move towards the east, please, Zach, and if that's possible.
Sure.
On a short transit, just above the seafloor.
How far are you wanting to go?
I mean, on the order of... Could we go up to 100 meters, or is that not feasible?
Are you going to want to come back?
No.
Okay, yeah. When we start boat move, we'll move 100 meters.
So these features that you're seeing on the seafloor, this is Dr. Becky Totten from University
Pretty
of
jolly.
Okay.
Got a new
These
move for
features
you.
that you're seeing on the seafloor are ripples that are formed when you have currents flowing over the surface of the seabed, reorganizing those sediments, oftentimes carrying away the lighter particles like clay and mud and leaving behind sand-sized particles. And one of the things that we were debating today, right, Seb, was whether these ripples are active or not. And I think from this view, we can see quite clearly some of these wider grains that are likely pumice from recent eruptions that are lighter, less dense than the surrounding sediments, those darker colored sediments, that they're actually moving. We can actually see them moving from one crest of a ripple to the next. Right here, you can actually see those particles moving. So that tells us a lot about this system, that we actually have active bed forms on the seabed, and we can see them at the sort of tens of centimeter scale here with the ROV, but we can actually see them at a much larger scale with the geophysical imaging that we're doing from the ship. Right, Seb?
That's right. Yeah, we can see. So yeah, you were just. I don't know if I introduced Becky Totten there from the University of Alabama, who was just talking to you about the biology and some of these ripple features. So she sat just behind me, and we're working together with colleagues from a whole range of institutions, several in Chile, several of whom are also in the room with us now. So yeah, as Becky says, we're just on a bit of a transect, and we're heading towards the east here. Still trying to get a handle on the orientation of those ripples, Becky, because if we're moving eastwards, they were
east-west.
They were east-west in terms of
first
the sort of ridge of those ripples. Yeah. So that's north-south transport. At least in that zone here. Okay.
Oh, this is
so
very
this is
different.
slightly distinctive. Maybe we could just pause here, please. Zach. So we've just come upon something slightly distinctive in terms of colour, and I think it's pretty difficult to interpret sort of everything we're seeing in the geophysical data. We can see structures, but we can see them at the resolution of sort of meter to 10 meter scale. So we can never be quite sure what we'll see on the seabed when we're down sort of centimeter scale, or indeed when we might try and core something. I don't know what you think, Becky, but I think this is worth a scoop.
A scoop, yes.
To see this environment, and then maybe we'll carry on the transect. I think the pale part, please. Thank you. Now, to me, what I can see, for those who've got logging here, this looks eroded into a sort of blocky, almost slab-like pattern. It's a layer of what looks fine sand to mud to me. Can you see it slightly? It looks sort of horizontally layered. You can see some stratification where it's been eroding. So this looks like I might interpret this as a sort of an earlier deposit that has since been eroded away by currents, and we're seeing a sort of relic that's preserved between these sort of rocky pebbles.
Yeah, it almost looks like these rocky pebbles are collecting where that erosive surface is lower than the rest of the surface there, where you have kind of these lower features, or maybe that they're also helping
it's sort
focus
of preserved
flow.
in sort of hollows in the pebbly side of the bit. So we'll have to sort of look at this carefully. It's not a type of material we've seen on this dive so far, or indeed on the dive yesterday. So it'll be interesting to contrast this with the dark sand that seems to be dominant here, where we see something on top of these pebbles, the dark sand. For whatever reason here, we don't see that dark sand. Is it pretty?
It's almost like a rock.
Is it pretty firm?
Yeah.
This is hard. Okay.
Like a sand.
Okay, that's intriguing. Right. So this is much harder than we thought from the imagery. So it looks fine grained to me in terms of its geological characteristics, or relatively fine grained. But could
also be. I see two possibilities here. It could be, something very hard, like we know We have some hard, older surfaces here. Because when clay compacts, it becomes very sticky and very hard to erode and very hard to dig into, which is what we're trying to do right now.
So, as Becky was saying, it appears to have a relationship here with this pebbly unit. We might have to. We can certainly see places on the view on the left where the pebbles seem to be on top of this. If you look on this view, so this material, at least here, appears to be underlying some of these pebbles, like you're saying. So this is interesting. It's, as Becky says, it's sort of cohesive or consolidated. Regardless, it's forming something that isn't being particularly readily eroded by these seafloor currents. And if that's the case, given its relationships with the pebbles, we'd interpret this as something older than that superficial sand, which is picking up the ripples and appears to be the sort of present active sediment on the seabed. So Zach, we're struggling to get this, do you think? If it's sort of...
Yeah, and kind of can break it up, but it's like really not a quick process.
In the finer spots.
Do you want to try with the fiber
Oh, that would be risky.
I think it's very
Just to see this.
I would carry
Try.
on the transect, I think,
Okay.
if we can't grab this.
Okay.
What do you think?
Carry on. I'm skeptical that if a metal scoop bag doesn't pick it up, that a push core won't either,
Yeah, but it's been
which is
successful.
plastic.
It's hard, I think.
It's hard?
Seems
Do you
to
think
be
the
a
push
very
core
hard
would get into this,
surface.
Zach?
We can certainly try. I'll tell you in 5 minutes.
Because
So I will just add here for the audience, this is not what we
Yeah.
expected.
Yeah,
And this
got some
is
in there.
the really amazing part of doing this research with the ROV. We usually can't see the seafloor at all. We just send coring devices to get the surface of the seafloor blindly through the water column and bring them back up and see what they look like. But here we're actually able to have a view of the seafloor. Right now we're kind of troubleshooting how to take a sample of it. So this is a very new, novel technique that you're watching in action right now, and made possible only because Schmidt Ocean Institute has supported this research and has had engineers and techs on this problem helping build devices so that we can do this unique sampling of the seafloor. This is super, super rare to be able to do what we're doing. Any geologists in the room, I think, would agree that this is a great luxury that's very new to us.
We've moved about 30 meters.
So, yeah, see, I got a little something.
Okay, so we try to pick up some of the seafloor with the robotic arm.
Oh, that's good.
And we have Zach operating the arm right now. Zach and Claude are
I put it in there.
flying the ROV, operating the ROV at the moment.
Orientation for this pebble?
Not for the pebbles.
We're in very
No, we just
capable
yeah,
robotic
there is an alignment
hands.
here,
Aligned
but
there.
we just came upon a patch like this. We haven't seen anything like this on the dive so far. We started off with rippled sands, black sands, with
They were
pale lags, dark sands, like yesterday, but with more white material and what looks like coarser white material.
That way material
Zach,
is-
Zach, change here. We are in position now.
There's pumice as well.
This pumice, and you can see that bed forms are active because you can actually
We
see
saw it moving.
the sediment moving from one ripple set.
They look like north-south transport
Wait,
to me.
and did we get the sense that the ripples were having like one material on one side and a different material on the this side?
Are you gonna
No,
wanna
we
stay
just
there
took
for
one
the also,
scoop.
Or are you gonna wanna move on?
Did you put that small piece in the box? I think we should carry on moving, please, to get a more of a
So one of the challenges here, why it sounds like we're rushed, is because we are. We're having to deal with pretty strong currents here. So we've been waiting to deploy the ROV until the currents are below a knot. It can't operate above that threshold. It's just not safe for the ROV, and how it's connected to the ship through what we call the umbilical. And so we have been waiting to get down. We waited until the current started lowering, deployed very quickly. And it's pretty shallow here, so it's only 140 meters water depth. which in terms of marine geology, that's shallow, so it didn't take much time to get to the seafloor. But we're trying to get as much sampled as we can before the currents pick back up, because we know that they will pick back up. Wow.
I mean, I think it
Wow.
material, but we could potentially try to do a vibrator.
Yeah. But you might bottom out in that hard unit. That might be why we didn't get far yesterday.
Wow, looks like a dune.
So we've come over a
These are what I mean by bed forms on the seafloor. So this is a sedimentologist's way of describing ripples and dunes that form from fluid flowing over a loose sediment bed, which can either be water or air. Dunes are the air fluid forming at the surface. Large dunes in aeolian environments, for example, wind-blown sediments. They can also, similar features can also often also form on the seafloor and on riverbeds and channels, wherever you have this increase velocity of the fluid over the surface, depending upon the size of those particles. It will move those particles and rearrange them into these cool forms, these ripples that we're seeing here.
Yeah.
One of the really interesting things too is that we have different kinds of particles.
Get an understanding.
So the lighter particles from the samples that we brought up yesterday, we identified as being pumice from the recent eruptions, very characteristic of the 2015 Calbuco eruption, to have this whitish colored pumice. And of course, pumice, as we all know, has these preserved air bubbles in it, so it's always going to be less dense than other rocks. And so you can see it's at the surface here. It's moving more easily. You can even see grains rolling up the back of this ripple right here, and then sliding down. So those whitish grains are lighter. They're less dense, and so they're moving more easily.
So the white stuff there is not just.
Whereas the darker grains are more dense.
This white stuff? I don't think so. I think this is pumice. And biological. I'll show you the sample we picked yesterday. It's a mix. It's full of crystals as well, and dark lithics. It's a mixed volcanic bioclastic sand.
So what you can hear now is Dr. Seb Watt from University of Birmingham in the UK, and Dr. Rodrigo Fernandez from Universidad de Chile in Santiago, talking about what we observed yesterday, what we pulled up from the
This
ROV,
feature is not so clear. Yeah.
and the different lithologies, meaning rock types, that we observed from those samples. It was actually pretty mixed. So we don't only have these volcanic clasts, we also have mixed lithologies that indicate that we have erosion from the pre-existing landscape. We have metamorphic rocks, we have all kinds of, polished rocks that may be transported during glaciations that made their way out into this basin. And then, of course, like what we're looking at here, a lot of volcanic clastics. Anything to add there, Seb?
No, sorry, Becky. I was, watching the live recording, but I think you've just been giving an introduction, right, to what we're sampling here and so on. Mm-hmm. I was just looking at Diego, because I see Eulogio has just joined the chat.
Oh, Eulogio is here.
Eulogio's here,
So one of the collaborators, very important collaborators on this project is Dr. Eulogio Soto from Universidad de Valparaiso. And two of his students are here, Diego and Gianluca. Diego's waving. He's waving to you, Eulogio. We've been collecting a lot of samples to bring back to your lab. I think you'll be quite pleased. Yeah, been working hard. And I don't know if we shared on the YouTube yesterday, but if anyone wants to go back and watch that dive stream later, I think it's available right now. But we had sampled a large pink Medusa-looking organism that's actually an echinoderm. It's called Gorganocephalus chilensis. So endemic to Chile, and we all really enjoyed looking at it. The crew came and checked it out. Yeah, we're all very excited about some of the organisms we collected from the seafloor yesterday. So Dr. Soto's group is all studying the middle and large size fauna that we find here. The meiofauna, that's a middle size fauna, that's just our fancy word for it, and the macrofauna, the larger size fauna. Here today, I think we can use that information of what we observed today to inform the record of past environments that we're collecting with these sediment cores. All right, so we are turning on the vibracore. We are shaking the vibracore, basically just vibrating it so that the sediment, it basically loosens up the sediment. It creates what we call a standing wave in that sediment. So that, this is looking a lot better than yesterday. We're getting a little bit better penetration. But so it will make that sediment act more like a fluid so that you can actually push your core, your metal tube, deeper into the subsurface and collect more. Interested in these layers of those layers are like pages of a book. They give us an indication of time. So we're trying to open up this book here offshore of the Rayas Delta in northern Patagonia in southern Chile and see what we can find about the past eruptions here, past volcanic eruptions, how those eruptive events are expressed in the marine environment, how they're preserved here, and then, very importantly, how the ecosystems responded to it.
Okay, so we know how much longer. Yeah, okay. Yeah, thanks. You say when we have to... So we're just discussing the duration of this dive. Got really nice images of all the glass here. Yeah. We're in a pretty confined channel offshore the Rayas Delta. We've got this river coming in, and we've got strong currents coming through this channel, strong ocean currents. So this really limits the timings of these dives, the time of day. We're having to go either side of high or low tide, and the duration of these dives. So having to be quite mindful of the currents and be sort of selecting our sites and choosing our sampling methods, because there's a sort of really limited time window for doing these. So I was just discussing that with the pilots here, who you can see just trying to lower this vibracore a little bit further into the sediment. And with an eye on those currents, we may have to go back up pretty soon. Is it going down again, Claude? Or?
No, it's still up. It's still low. It's just the direction is switched now. I mean, that's probably the start of it, you know.
You still managing to get in any further, or is it sort of bottomed out?
Not so good. Will it help if we just start jumping? Here,
Shake the whole ship,
Take down.
make a seismic wave.
Yeah, I don't think it's really going anymore. You want to stop? Pull it out.
How far did we?
Well, probably a good, at least a foot, I'd say. Yeah? Maybe a foot, something like that.
Do you want to give it one more go? Do you think it's when you stop to move that you sort of it's difficult to then do a second drive?
There, it just fell some more.
Okay.
It went
We saw
deeper?
that before, if you stop vibrating and then start again.
Yeah, because this is vibrating.
yeah.
This is what
Yeah.
we're designed for.
There we go.
Yeah, so this is the first cruise in which
So it
we
seems
have
to-
deployed the vibracore on the ROV Sebastian.
so- Okay.
So last time you can do it.
We've waited and waited for this
Go
moment.
ahead. We trust you.
We need to get this sand in our core.
Everybody is looking at you.
Give me a little more slack.
That's Dr. Fernandez encouraging the vibracore to...
Oh, it's going in. It's going in.
Yeah, let's stop and start.
Yeah, it's
Can
looking
you
good.
control the way you?
So this will give us an understanding of what these dune bed forms are comprised comprised of.
That might
They're quite substantial, so I think it's unlikely that this core will get right through to the base. And as we saw earlier, we seem to have a pebbly, sort of really very coarse base anyway in this region that these dune-like features are deposited upon. And these have forms that suggest strong sort of current movement. We've been looking at the maps of these this morning. Some seem active, some perhaps they're inactive, and are buried by late sediments. So, I think this could be quite an interesting core. It won't necessarily be the same material all the way down. This stuff we're seeing on the surface is not necessarily the stuff that this whole bed form is made of. That's something we'll have to evaluate when we open up these cores. This is looking pretty good, Zach. We see the cap already. Is this the 2-meter tube?
Yes.
That's pretty sweet. If at first you don't succeed with a vibrocore, shake it. Oh, shake it again.
Because we don't want to open this if we can get one.
Yes.
We just get one. I don't know if we have time for another one. It's hard to know. I mean, it could be all the same stuff,
Right.
or it could have. So we could just have 2 meters, but we don't know. It's hard to know. Yeah.
If we have time, we're gonna try.
Try. Maybe a shorter one. Because it's taken a while to get down on this one.
Well, we'd like to have at least, because this will be, if there's any changes, it will be like more or less like this.
Yeah.
So we'll need at least, how much?
I think so.
Close to a meter?
Yeah. Yeah, because we want to understand if these dunes are sort of entirely made of this stuff,
Right.
or if this stuff is a joint
Right,
on the surface. A bit hard to tell.
All right. Sort of stalling out here.
Stalling out there.
Yeah.
Okay.
Ready to pull it?
Okay. Approximately how far do you think you've got in there?
Well, I'd say probably at least a meter, huh?
Okay.
Come on.
So that'll be good to note for compression. So we think we've gone in about a meter, and then we can look at the core length when we recover it and see if we have about a meter or if there's compaction. But we would expect much less compaction than we've seen in the mud-rich sediments.
Yes.
This stuff is not going to, I don't think.
Yeah, sand. It's very hard to compact sand.
There's like a black line on that
No.
tube.
Yeah.
If it's actually compressing, then we need to rewrite the books.
Yeah.
Yeah, we have to
Construction
rewrite
process.
the laws of physics.
So there's a black line on there, guys, and that was below the sand. So when it's on deck, you should be able to tell at least.
Okay, so
at least
The
up to
black
That
line.
black line was very, yeah. So
Awesome.
You guys put that?
Yeah.
it's quite helpful to
Fantastic.
It's quite helpful to note this because so we can gauge when we're doing the vibrocoring what our expected length is
Yeah.
from what we can see, and then we compare it with what we recover. So for those listening, we've been finding that in our muddier sediments that we've been coring on previous dives, we're getting a lot of, or we think we're getting a lot of compaction of those sediments. So what we recover is a much shorter core from what it looks like it would be from how far the tube went in.
We're also seeing Dr. Matt Lee joining from Puerto Montt.
Really?
Yeah, look, he
Oh, hi, Matt.
says
Yeah,
he's
yeah.
asking about a mudstone we were trying to sample. Ooh, it looks
yeah.
like those that they find in the intertidal
Yeah,
area
yeah.
around Puerto
Okay.
Montt.
Interesting.
Yeah. Do you want to say anything, John? John Lucas standing up. We're Eulogio Soto and Matthew Lee are very close collaborators on this project, both biologists studying the polychaetes and the nematode worms, respectively, but curiosity for all organisms and the substrates that they live in. You want to say anything, John Luca? Did you want to answer his question?
Again, Matthew?
Do you think it looks like? I think if it's looking like what you're seeing in the intertidal zone, yeah, it could be that you have this clay that it's sort of compacted and not loose and fluffy like what we've been seeing before. And whenever you have really compact clays, Because clays, and some clays are even more cohesive than others. They have different properties. Different clay minerals have different properties. But whenever you compact clays,
You can feel it's heavy, yeah?
they become really, really, really sticky and hard to erode. So we've been talking about how the water traveling over the seabed can move sediments. You can imagine if it's loose, fluffy clay, like what we saw at some of our first dive sites in Rellenkavi Fjord, that it would move that clay really easily, right? But if you have compacted clay, because it's so sticky or cohesive, it becomes almost like a hard surface. It becomes really, really difficult to pick that up. And sometimes it only gets picked up when you have high energy events, so really, really high current flow events where you might actually rip up clasts of the seafloor, rip up pieces of whole chunks of clay.
So Matt's just put a description of what those mudstones look like, and I agree, Matt, the properties of what we were seeing. So it's sort of solid, and you can see the layering,
but you can break it up with your hands. Yeah. So, and then we kind of did that with Sebastian's hands.
Yeah, exactly. We got another interesting question here about have we found any man-made objects like pottery or plastics and so on.
Good question.
I mean, it is a good question, and fine-scale plastics, tiny fragments of plastic is certainly something that'd be interesting if there's evidence of.
Yeah. And
we've only just started looking at these, but on the sands last night, I didn't immediately spot anything.
Yeah, well, here's the deal about plastics, okay? It's really, really hard to sample for plastics in the ocean. You can do it. Certainly there are several groups around the world who do this, but you need to be extra careful that you don't contaminate those samples with your sampling devices. That's pretty common, actually. So we use plastic bags, plastic spatulas, plastic core tubes to collect these samples. So we won't be looking necessarily for microplastics in these samples because of the worry for contamination. If we wanted to do a microplastic study, we would design it a little bit differently than what we are doing now. But we're actually interested more in trace metals because of the volcanic influence here. So because we're interested in trace metals with those push cores that we collected earlier in the cruise, we've been using all plastic to sample so that we don't contaminate with metals. So it is quite a challenge to sample for everything, and we had to prioritize and prioritize based upon our areas of expertise. So we're not looking for plastics. We have not seen anything like pottery or archaeological or cultural artifacts. That's not to say that they could not be here, but we've not observed anything like that here.
No, I mean, something interesting about Chai 10 actually is it's a source of obsidian. And one of the few sources in this part of, the main source in southern Chile.
Yeah. And what is obsidian?
So obsidian is basically the equivalent of this white pumice that I think is what we're seeing here, but without all the space in it.
Mm-hmm.
So it's volcanic glass. It's silica-rich volcanic glass, so a rock type called rhyolite commonly, and the volcanic the magma erupted by Chai 10 is of a rhyolitic composition. If that's full of bubbles, and that's what ultimately drives the explosive eruptive behavior, then those fragments will be frothy. They sort of will be foamed up through bubble expansion. That's literally what drives the explosive eruptive process, the acceleration of that magma and the fragmentation of that magma. But if that gas is lost, then that magma is gas poor, and it will come out as a dense, highly viscous liquid magma, which does not crystallize and quenches as a volcanic glass. So it's not glassy because it's cooled very quickly, but it's glassy because its crystallization is inhibited. So it is a glassy volcanic rock, very distinctive, black, glossy, with a sort of rounded fracture pattern typical of glass, if you can picture that on sort of broken glass where it chips off. So that's a material called obsidian. And because it fractures in that way, when you break it off, it can be fractured and sort of chipped to make sharp tools. So this was a useful material to make stone tools from. And artifacts of obsidian tools from Chaitén have been found right along this coastline in this part of Chile. I believe quite extensively, although I need to read up the papers on that. But my understanding is this is a significant source of obsidian and has been a source of stone tools for, going back many thousands of years, I think. So another interesting feature of Chaitén volcano in this region.
Very cool, Seb. And so we just had a visitor from someone who's been living and breathing geophysics nonstop. Our other co-PI, our other fearless leader, Giulia Matilda Ferrante from OGS in Italy.
Yes.
Why don't you introduce yourself and tell us what you've been doing?
Yes, so I'm leading the geophysics group here on board, and we are doing a lot of bathymetry and high-resolution seismic with a sub-bottom profiler, which is a very cool instrument, especially the one that we have here on board the Falcor. And we want to help in selecting the sites for the rock dives and the cores and all the sediment sampling, and we are also studying the morphology and all the processes related to the seabed and to the first tens of meters below the seabed using our data. And together with the bathymetry, we also collect water column data, but especially we collect backscatter data, which is something that is particularly helpful in this case, especially for these dives. And the backscatter, for who is familiar with it, is another kind of sonar measurements, and it measures the amount of energy scattered back from the seafloor, and this should reflect the physical properties of the material on the seafloor, lying on the top of the seafloor. But when we have dunes, like here in a deltaic environment, the geometry of the dunes can affect the backscatter. So I came here actually to discuss with Rodrigo that we should have met, I guess, about how to remove this geomorphological effect, so a geometrical effect from the backscatter, to have only the response about the type of material that we have here, which is the thing that we are interested in for the sampling and also for the coring, because we cannot risk to bend the core in a material that endanger the core tube. So we were in the middle of a conversation about how to separate the two effects from the backscatter. And with indirect measurements, you always have this problem. So you really need to what you normally do at home. It's difficult to do it during the cruise on board. Is you separate the effects, modeling them separately, and subtracting the models from the real data. So this is something we will definitely try to do at home, but we were looking for something that we can do here now, and because we don't have the rock dive to show us with a camera what is on the seabed all the time. And for the core, for example, we will go. In general, we would go blind. In our cruise, we are lucky, and we can.
Blind.
In our cruise, we are lucky because we can decide to core the same location that the dive showed us. And this is geophysics. It's nice because it gives you a very broad view of the subsurface, so kilometers long profiles and tens of meters deep images.
It's the first
2D.
site that we have before we send these gears to the subsurface, the surface of the seafloor. And we actually do this. Sebastian is able also to do geophysics actually, because it has a multi-beam mounted on it. I don't know if many
and
people
free,
know that
yeah.
you can collect images of the seafloor from the ROV Sebastian itself.
Yeah, they have a Kongsberg M3 with a crazy resolution of, I think it goes, I don't know, maybe like 250 centimeters, something like that.
Depending on how high you are.
Or depending on how you are, and the recommended, let's say, swimming height, it's around 50 meters, and we are gonna try that definitely to have super high resolution images of the seafloor at the dive location or at the ROV location. The problem with that is it's gonna be lots of data, and
we don't have time to process. The data.
No, these data we will definitely process them on shore, but when we are sure. Yeah.
So, what Matilda does is a lot of coding, a lot of creative coding. Can you tell us, especially for the kids in the audience, I think my kids are in the audience, how you got into this career path, how you learned how to code and learn that this was something that you really wanted to do for a career? Go in the middle of nowhere on a research vessel, collect data where no one has collected data before, and produce these amazing images of the seafloor through your computer skills.
Yeah. Well, in my opinion, what we do here now, it's maybe the last bit of exploration that we can do on the planet. So since we really have investigated land in any direction and we still miss a lot of the seabed, what we are doing here now, it's maybe a bit similar to what explorators were doing in the past centuries. And coming from physics, the acoustics and geophysics, it was the most natural way for me to approach all of this. So I studied physics at university, but at some point I realized that I didn't want to stay in front of the computer the whole day, and I didn't want to stay underground in a lab or in darkness the whole day. So I wanted to stay out. And so geophysics and earth science, it's definitely a good idea to do that. So with a PhD, I moved to signal processing, which is something very useful for all the geophysical measurements, acoustic normally measurements, but also magnetics, gravimetrics. We can use a lot of stuff. And from signal processing, I passed to seismics data and slowly approach geology, which is a complicated subject if you haven't studied it. Like
it's complicated,
me.
But
yeah.
I mean, not everybody can. Very few people actually can do what you do, and making the magic happen.
Something in
between.
Something in between.
Both are very important and complementary.
Yeah. Well, of course you cannot know everything, but this is the point about having a large team and with all the different skills represented, and so we all know what are we all together we have the touch on what are the actual problems and so on. And for geophysical data set, coming back to coding and so on, a major issue is how to analyze them, because these are normally a huge amount of data. If you think about a sub-bottom profile that you can imagine, in general, like, I don't know, 20 kilometers long, even less, let's say even 10 kilometers long, these are tens of thousands of traces, so you need to analyze them numerically, of course. So the signal processing is numerical and must be optimized. There are a lot of softwares to do that, and the best one, of course, are the commercial one, developed by the industry, especially the oil and gas industry, and these are very expensive, and you need to bring licenses with you, and so on. So a way to get around this is to write your own codes, at least for doing the first processing on board that you need. And well, there are libraries, for example, in Python, which is a language that I personally use a lot because I find it
Would you
bit more
recommend
simple.
to the kids out there to learn
Definitely,
Python?
definitely.
Learn
I mean,
Python.
if you learn it,
Yeah.
the young, if you learn it when you're very, very young, it's gonna be easier for you, and it's gonna be a tool that you have forever. It's like knowing a language, but it's a universal language.
It's just a language,
Yeah,
just another
yeah.
language.
It's another language, and this is how you can talk with a computer, basically. So you can make it do what you want, and this is pretty powerful. And with geophysical data, we are basically talking about, yes, signal processing, but image processing. This is not so much the filter I apply to my data are not that. In the end, are the same, are similar algorithm to the filters that you can use on Instagram, for example. These are images, the recognition algorithm, imaging, let's say, removal of noise, filtering out stuff, and so on. So it's, I mean.
So you can see the features better, right? So that we can have these images of the seafloor that are easier to interpret.
Yeah, and you can see the past. I mean, with seismics data, I mean, so bottom data you don't have such a big penetration.
So the sub-bottom data is literally below the bottom of the seafloor, showing all the layers.
It's like an ecography or a radiography of the seabed. So you see a section of it, what is below. You see the water, you see the seabed, and you see what is below. And depending on the source that you're using, so on the amount of energy and on the frequency of this energy source, and on what are you using to listen to the signal that is reflected back, you can see deeper and deeper and deeper. In this case, we are interested in the very shallow structure under the seabed, some tens of meters, so we use a sub-bottom profiler.
Can you tell a young man named Leo that he needs to learn Python so he can
Leo,
code for his mother?
Leo, Python is fun. It's actually very fun, and it's very useful, and you can do lots of stuff with that. Yeah.
It's very cool.
Yeah. It's very cool. It's very.
You can
cool.
help mom with her work.
Yeah, that's also true, and you will be an hero for everyone. It's for people that don't know how to code. Coding is like magic, so it's something. It's really useful for anything in your life. Once you know how to code, you use it for everything. I mean, everything.
And Matilda, you're from Trieste. That's where you're working now.
I'm working in Trieste,
for the survey there, the geological survey in Italy. Where did you go to school in Italy?
I was born in Florence. I went to school in Florence and Firenze, yes. But I did my university path in Trieste because it's a very good place where to study physics. There are several research institutions in several different fields of physics. There is an accelerometer, there is an observatory, there is a synchrotron, and there is the Italian Institution of Oceanography and Applied Geophysics, which is where I work. And it's a beautiful city, by the way.
Awesome. Yeah. Maybe Leo one day could study in Italy.
Yeah, why not?
No ground faults or anything there? Still power on?
He's been there.
Good.
His family there.
Cool, thank you.
Awesome.
Tips for becoming a marine biologist? This I don't know. I'll pass the word to someone else. It looks really cool as well.
Thank you. Thank you, Matilda. Grazie mille.
Prego.
And so now I'm going to pass the baton back to Seb to tell us where we are going with the Sebastian now.
Okay, yeah, so I guess for those of you looking at this online, you're maybe wondering what we're currently doing. I don't actually know how much you can sort of hear of the conversations here. You might have had quite a lot of voices coming through as the words. Sorry, we're doing the transect.
Oogly boogly.
So, I mean, all of this is what we're seeing when we see the seabed. This is really informative, really helps us interpret what we're talking about. But for the last 5-10 minutes, you'll have seen higher up in the water column, so you probably couldn't see anything at all. The reason we were doing that is we lifted it up so we could map this tube using the base of the
Look at the spacing. Can you note the spacing?
The higher frequency couldn't have a large area seafloor effect. Yeah, we can just go up to sort of crest. Yeah.
Those linear features are amazing. Those are the ripples that we've been talking about. The crests, again, have this wider colored pumice clasts that are lighter. You can see how linear they are.
So yeah, we're lifting up to do that mapping because you get a sort of an angle. When I got in, sort of restraint from the base of your mapping above and on top of that determines the strip of your mapping. So we had to lift up a few tens of meters, and just 30 meters seafloor, so quite a narrow stripe across this dune feature, but it will allow us to understand its properties and its wavelength and to look at it in much higher resolution than we can with the from the ship itself. So the imagery from the ship itself was a really good sort of map of the seafloor with a width, depending on water depth, but here a few hundred meters, up to a kilometre, slightly as the water gets slightly deeper. But the resolution of that is on the order of 40 meters, so that should be sort of
Just scooping, but yeah, we took one fiber.
whereas the RV we can collect much more detailed picture, but much narrower.
Just fiber
So
core
that's
and
the reason
scoops.
we were looking to do that. Now we just come down, or we're just trying to look at something on that imagery, technical setup, I think. So we're just making use of that time to collect the scoop of the location. So I'll have some material with the scoop, we can grab it on board.
Is this scoop 3?
Scoop 3,
Yeah.
okay.
I'm just asking.
I was
4, scoop 4, thank you.
Okay, is that, have you got any more scoop bags empty? That's all. Yeah. Because you have one. Fully scooped. Yeah. Cool. Okay. How we?
Ready?
You want to try the transit? You ready for?
We need to try the transfer and if we can get
Higher up the
yes,
seafloor?
we're getting 2 meters.
Yeah. Okay. So. Good. How high is the seafloor?
Which number of scoop back?
We started last July, 2
You go 50 above the seafloor?
Yeah, see how that works.
Is that possible in this water?
Oh, just to answer the question in the chat, yes, we're on the Pacific Ocean side of South America. We're in a place called Patagonia, in southern Chile. We're in the northern side of Patagonia, and we are exploring offshore of some deltas that drain areas with prominent volcanoes that have had recent eruptions, namely the Calbuco eruption of 2015. That's what we're most interested in here. Of course, we're also exploring 2008's Chaiten eruption. And then we will, we will continue south from here. We started in the northernmost part of the sort of oceanic component of northern Patagonia in Reloncaví Fjord. And no, we're not in Reloncaví anymore. We have moved southward. Thank you for asking that question, Gabriel. We've moved southward, and so now we're offshore of the Rayas Delta, And yeah, Seb, do you want to explain what we're doing now?
So you have just joined us, yes, here we are. Yeah, so the Rayas Delta is a river system that drains north of the Chaiten volcano. It also actually drains another volcano called Schmidt, which is adjacent to Chaiten. So a lot of active volcanoes in southern Chile, and they're strung along in this part of Chile, along the coastline, generally sort of within 10, 20 kilometers of the coast. So that means pretty short river systems can carry material from those volcanoes before they reach the shoreline. So they're not sort of immediately on the coast, but they're only a short way inland. And what this meant in 2008, when Chaiten had a large explosive eruption, was that the material dumped by that eruption on the landscape. So this explosive eruption injected a column of fragmented volcanic material, and then that
was really
back to the
coarse.
surface and draped the hillsides around Chaiten. So all that loose material was rapidly remobilized, rapidly carried down by rainfall into the
Transect real quick, and I think
and deposited huge volumes of sediment at the mouth of those systems, SOI deltas, and we're interested here in the impacts of that inundation of material.
They can't hear
in the
us.
marine environment.
Are we turned off?
No, you're on.
somehow like.
It says they can't hear. They say they can't hear.
I think it might be mine. Yeah, it's on.
You got -70.
No, you're on.
I can hear you.
They're saying they can't hear.
Maybe it's a problem on his side.
Try pulling the tight.
Okay. Yeah.
Okay.
So hopefully you could pick up some of that anyway. So yeah, just to go back to it. So we're now offshore this river system that drains Chaiten, and we're about a kilometre or so off the delta here of the Rayas River Delta. So we're likely seeing, we think, but we'll have to interpret this. On the surface, we're likely seeing sediment from the, at least that's been contributed to from the 2008 eruption of Chaiten. No, it's still struggling to hear. So apologies for the microscope issues. Becky, maybe you can...
Okay, can you hear me? This is cool to be interacting with people from everywhere around the world. There might be a delay. We are in the middle of nowhere. Yeah, hopefully they can pick up something. Okay, they said that's much better, so should I just pass my mic on to you? Yeah, you want to finish explaining the volcanic history and what we're doing?
Okay, yeah, so apologies for any repetition for those who might have heard this earlier, but just a bit of background on the location. So we're about a kilometre offshore the Rayas River Delta here, and this was a river system that was significantly impacted by the Chaiten volcanic eruption in 2008. That was an explosive volcanic eruption which produced large volumes of fragmented magma, everything from what we call ash size, so that's like sort of very, very fine sand through to sort of sand grade material, and coarser material, so blocks and sort of gravel sized fragments of pumice. All this material produced by the explosive eruption went up into the atmosphere and then fell back to the Earth's surface and draped the surrounding hillsides. That then got carried down by rainfall. It's a wet climate here in southern Chile, carried down into the surrounding river systems, and that huge influx of sediment overwhelmed these river systems, and we saw extremely large volumes of sediment deposited very rapidly at the mouth of these rivers, building out deltas, which in the town of Chaiten itself, which is about 10 kilometers from the volcano, inundated the town, sort of devastated the town, which had been evacuated by this point, recognizing the risk of this sediment inundation. So it had very dramatic consequences in this region. But what hasn't been studied is the consequences on the marine environment, or indeed how these events are recorded in marine geological records. And that's really what we're interested in this project. So those consequences could be biological, they could have chemical consequences. They of course change the morphology of the seabed with this deposits of these sediment. So we're exploring all these sort of facets of the impacts of this event.
Yeah, well, the float's right next to the boat.
Are they?
Yeah.
Okay. I'll do that. All right, so launch recover move.
Okay, so we're on our way back up.
And the float's already on surface. Sam, would you like to do an outro for the dive, or do you want me to do it?
Okay, so we're just coming to an end now, but hopefully you've got an idea of where we are. We're in pretty shallow water here, so we're really...
I'm releasing control. Both out haulers are on.
I've got control. I'm in normal. Hard to the bow.
Yep. Bridge, RV.
We need a sound. I want to push it.
RV bridge.
Can we start moving north at, let's start with the point 8.
North point 8.
Due north point 8, thank you.
That should help out when they get
All right, things change pretty fast around here. We're already off bottom, and the floats are on surface, and we are recovering the ROV now. And we're hoping to see you very soon in a couple hours once we get these cores processed for another dive. So subscribe with your notifications on, and you'll be the first ones to know when we're back in the water. All right, take care.
Why would all of a sudden